Okay, so today we are in the n factorial garden, and we are going to the second part of this garden is bijection, very useful between permutation and what we call Laguerre history. So Laguerre is a flavor of Laguerre polynomial in this bijection. So definition of a Laguerre history. History is a flavor, you remember everything you have done, like we have done for inversion number or maj, where you remember the choice you have done. So a Laguerre history is a pair where gamma is a Motzkin path. And C is a coloring of the E step in blue and red. So what we have gamma C is a two-colored Motzkin path, which we have seen in chapter on the Catalan garden, and such paths of length n are counted by Catalan number n plus 1. Now f is a choice function, is defined the following way. I put some weight, some valuation in each step of the two-color Motzkin path. If I am at level k, the minimum level is 0. So if I am at level k, then I put a weight, ak equal k plus 1. If I am in a blue or red level, I put a weight b prime k, b double prime k equal k plus 1 also. And if I go down, I put a weight ck equal k plus 1. So everywhere the weight is k plus 1, where k is a level of the starting point of the elementary step. So here, for example, I put in yellow, the yellow number 1, 2, 2, 3, 2, 1, 2, 2 is going to be this number k plus 1, k plus 1, k plus 1, k plus 1. This number, I am at height 2, so I put k plus 1 equals 3. So once I have defined this weight, this valuation, v of omega I means it's the weight of the step number I in the path omega. Or omega is gamma in that case. Omega is gamma c. So this is the two-color Motzkin path. For the step number I, there is a weight, which is k plus 1. And then the function f, the choice function, is any numbers, pi, p for possibility, any number between 1 and the maximum possible, which is the weight of the elementary step. So for example here, I choose the blue numbers. For each elementary step of the two-color Motzkin path, there is a blue numbers, and these blue numbers are any numbers between 1 and the maximum possible, which is the yellow numbers, which is k plus 1. So you see you have two things. You have the path, the color, the two-color Motzkin path, and then some weight, which in that case, as everywhere, is the same, but we will see some other paths with the weight is different. And then the function f, possibility of choice function, any numbers between 1 and the weight of the elementary step, which is 1 plus the height of the starting point of the step. And now I claim that such Laguerre history are enumerated by n plus 1 factorial. So we are in the garden of permutation. So there must be a bijection between such Laguerre history and permutation. And this is the main bijection for today, which can be, there will be special case, and which is related to the theory of orthogonal polynomial. So first, description of the bijection with binary tree. From Laguerre history, I'm going to permutation. So I am going to construct an increasing binary tree from the Laguerre history. So I start from the first step of the path. So I put a 1. And because it's going up, I put two external edges to the left and to the right. Now I'm going to insert the 2 in the binary tree. So there is two possible positions. And these blue numbers tell me take position number 2. The yellow number give me the number of possibility to put the 2. And you have to choose which one you put. You can put 1 or 2. So you are going to label the empty position, possible position, from left to right. So this is the first position. Second position. The history tell me, okay, take the second position. So I put the 2 in second position. Now why I put a left edges, only left edges on the 2? Because it's a level red. When it's a level, the number of empty positions for the next step remain invariant. If it's a red step, you go on the left. If it's a blue step, you go on the right. Now the 3, I have 2 positions, the yellow numbers, and told me put position number 2. So I put the 3. The 3 is going up, the step of the path is going up. So I open 2 new edges. And now I have 3 possible positions for the next one, and I am a height, 1 plus the height is 3. And I put it in the second position, the 3. Now the 4, put the 4 in first position. So this is the first position. Put the 4 here. And now we are going down on the path. So the rule is that when you go down, you don't open any new edges, which means the number of open positions decrease by 1. So each time the number of open positions is going to be invariant if it's a level. Increase by 1 if you go up in the path. Decrease by 1 if you go down in the path. Now the 5, there is 2 positions. Position number 2. And the 5 is going down in the step, so I don't open any new position. Now I have only 1 possible position. And for the 6, I take a blue level, so I put white edges. The 7, I'm going up with only 1 possibility, and so I open 2 new positions. And the 8, take the second position and go down. So I stop here, and then what remains at the end is an empty position. Because at the beginning there was an empty position. So I finish with a 9 to fill up. And what I get in an increasing binary tree on n plus 1 vertices, n equal 8, n plus 1 equal 9. And so what I get from the Laguerre history, increasing binary tree, so by the projection we have seen last time, we get a permutation. By projection, we have seen,
what
yes.
is the second position? When you said put something...
Second position.
It's to the right.
Left to right.
Left to right.
From left to right, you label the...
I mean, you read, I guess, left.
From left to right in the...
So how do you decide which vertex to put it under?
Here, for example, I put the 1, 2, 3, the 5,
Yeah.
1, 2, 3, 4, I put the 5 in the second position.
Under the third.
Second position, first one, second one. So you put the 5 here. So I get a bijection between Laguerre history and permutation going through the increasing binary tree. So this is the Laguerre history here, this is increasing binary tree, and this is the projection, the permutation. Because it's a main bijection, I will describe a second description with words. In fact, this bijection was done with my colleague François more than 30 years ago, and when we make the paper, we do this description. No, we do with binary tree. The referee was not happy, so he asked us to do with words. And then our colleague, like Flageolet, was not happy. They asked, why you don't put in trees? It's much... so when I put both description, you will choose which one you like. In trees, in words. In words, it's a direct... we are going to get directly the weighted path with the permutation. So I start again the same description. In fact, the same description is each time I take the projection of the partial increasing binary tree. So let's do it again. So you start with an empty cell, like this. I put the 1. So the first value, the path is going up. So I put the 1 in this empty cell. In first position, there is only 1 possibility. And then it's going up. So I create 2 new empty cells on left consecutive to the left of the 1 and the left of the 1. Now the 2. I put 2 in the second position, so they are labeled from left to right. I put 2 here. Imagine you put 2 here, and then you open a new empty position on the left of 2. Just on the left, consecutive to 2, because it's a red. Then the 3 you are going up. Second position for the 3, I put the 3 here, because I go up, I create 2 new empty cells on the left and on the right of 3. So each time you insert I, and according to the 4 possible possibility of the elementary step, you don't create any new cell. Sometimes you create a new empty cell on the left, sometimes one on the right, and sometimes both left and right, but just close to the... So I put the 3 here, and I create 2 new empty cells. So the 4, yeah, I put it in the first position, and I don't create any new empty cell. The 5, I'm going down, I put the 5 in the second position, and I don't create any new empty cell. I put the 6 in the first position, there is only one position, and then you create a new empty cell on the right. I put a 7 in this unique position, I create 2 new empty cells left and right, and then at the end, I have only one empty cell, so what I have done is exactly the projection of that consecutive construction of the binary tree. And then at the end, you put the 9, and you get a permutation.
So this is a map from Laguerre histories to permutation?
Yes.
I think you said the opposite.
It's a map from, yes? Yes. From Laguerre to permutation. This was a reverse bijection, and you confused with the slides. Yes.
So that was exactly the in-order traversal of the tree in the previous construction.
Yes, it's exactly the same. At every stage,
The in-order,
the in-order of the binary tree give you this, and this means the leaves which are free, empty, you see. That is same. If I project this, I have 4 empty cell, 4, 1 empty cell, 3, 5, 2. So this is the in order of the. And I keep this. This is to remind you the whole time when we don't have only retro projector with the slides. You see. So this was when we have to put by hand everything, just to remind you of the whole time. There was no video projector, nothing. It's so you can still do the old-fashioned with the video projector. It's So now I have to show you the reciprocal bijection. So we start really from a permutation and get a Laguerre history. So just look when go back to the bijection from history to permutation. When you take the path. So the path, there is 4 possible steps. Each of these steps in the path correspond to 4 kinds of vertex. The leaf, the double vertex with 2 child, vertex with 1 child on the left, vertex with 1 child on the right. And this, if you look carefully at the permutation, this corresponds exactly to the classification of peak, valley, double rise, double descent. Because of the construction with the empty cell, and this is exact. So there is a correspondence between the classification of peak, valley, double rise, double descent in the permutation. I put the double descent in red, in red, and the double rise in blue, and the valley in green, and the peak in black. So these 4 possibilities exactly correspond to the path. So at least, if you give me a permutation, I can reconstruct the path gamma omega c, the path and the color of the step. At least I can do that. Now I have to reconstruct the blue numbers. So for this, I need a new definition. It's X decomposition of a permutation. It's not the X factorization. We have seen the X factorization with rho of X, lambda of X. Now it's something more delicate. The X decomposition. So you take a permutation on an element. You take any element X. And then the X decomposition, you see this. It's a sequence of blue and red word, U1, V1, U2, etc., etc. All the letters of UI of the blue are strictly less than X, and all the letters of Vj are bigger or equal to X. And the word, maybe U1 and UK plus 1 may be empty, but all this word, all the other words are non-empty. So you can imagine, first give an example. Let's take the sigma permutation I get from the bijection, the previous bijection. So here is a decomposition, U1 empty, V1, U2, V2, U3 for x equals 3. If you take x equals 3, you see, so the red block are all the consecutive letters are bigger or equal to x. The blue blocks, all the letters are strictly less than x. So the visual image is this. You see, you put the height is the value of sigma of I, and here all these letters in red are bigger than x. All the letters here are bigger, and x belong to one of this vi. Here x belong to v2. So the rule I claim that f of x. I claim that f of x is exactly given by this. So pi equal j, the possibility pi will be equal to j if and only if the I is a letter of the block vj in the I decomposition of sigma. I give an example here, you see. If I take I equals 3, then P3, the possibility P index 3, is equal to 2. Because P3, 3, belongs, the letter 3, is the letter of the word V2. And just check. Check here that 3, the third step, P2 equal to. So for each letter I, you just look in which block of the decomposition it is, and then you get exactly the pi equal j. You get the possibility function. So I summarize this reverse bijection. So you start from a permutation and you get a Laguerre history. So as we have seen, the step number I of the two-column Motzkin path is exactly this 4 possibility according to I, the valley, peak, double rise, double descent. And then the possibility function, pi, is j, defined by this condition with the I decomposition. So you can completely reconstruct your history by this. So you can individually, you give me any value, then I can know which, well, if you look carefully at the algorithm, this become obvious then because when 3 was put in the algorithm, there was an empty cell, and all this value here, V2, the empty cell was the cell number 2, and all the value which happen to be inserted after the 3 are all bigger than the 3. So you can really easily show that the two maps are inverse each other. So some people, they don't like too much sometimes the position, this parameter that we are going to take the position of the time you insert the value x inside the permutation. So another way is to take that pi equal j is also defined by the following way. This is an equivalent way to define pi equal j without going through the whole history of the number choice and which choice you took. So j, pi equal j is 1 plus the number of triple a, b, i, having the pattern 3, 1, 2. So what does it mean? We have seen Catalan factorization, which avoid the pattern 3, 1, 2. But pattern 3, 1, 2, I should put a little, how do you say, tire here. I should put the Catalan permutation it's more general. Here, when I put 3, 1, means the two letters must be consecutive. And this one can be away of the other. So this means that there is a triple A, B, I, such as that A is sigma of k, B is sigma of k plus 1, I is sigma of L, and such as that, you see the pattern 3, 1, 2. So this is A is the biggest, is 3. It starts with the biggest. Then you have the middle, the smallest, B, which is here, and then I, which is between A and B. So proof, you see when I put I, Pi, the possibility I equal J, all these triple, see are exactly triple like this. When you change from a red word to a blue word, you are here, you are bigger than I, and you go down, you are smaller. And you have two consecutive letters. That's the only way you can have A and B consecutive, which are A bigger than I, and B smaller. So each of these green pattern is exactly the number of patterns which are on the left of I. And you have 3 patterns here. The number of patterns is exactly J. So the number of such transition between a red and a blue is exactly the number J, which is what the choice possibility, the index, V index J.
How is PI defined?
Pi, that was the possibility. Pi,
If I belongs to Bj, then it's defined Pi equals J.
Pi is to reconstruct from the permutation. I want to reconstruct the Laguerre history. And Laguerre history was a 2-column Hodgkin path and a sequence of possibility function, P1, P2, Pn. So I am defining Pi.
So it's defined Pi equals J if and only if I is a letter of Bj, right?
Yeah, yes, it was the first definition.
Yeah. If I belongs to Uj, what do you define?
Pi.
Is the I decomposition, so it will have to belong to V and not
By
to
definition, it belongs to V.
Pi is if I is a letter of Vj. Vj is the x in the I decomposition. I equals 3 here. It's a so you have to go back to the definition of the I decomposition. Here I equal x, the x decomposition, I decomposition. Example, this is a visual things, the x decomposition. And x belongs to Vi. It's going to mean that P, the possibility function P index x, is going to be equal to I. Sorry for the change of notation between I, J, and x. And then you get the first characterization of Pi, and then the second characterization of Pi with this picture. That means this 312 means that there exists 3 indices k, k plus 1, L, such that sigma of k equal A, sigma of k plus 1 equal B, and sigma of I equal L. No, sigma of L equal I. And such that, you see 3, 1, 2. The 3 is referring to the biggest value, which is A. 1 is referring to B. And 2 is referring to I. So when you read from left to right, you see A, B, I, such that it's if you reduce this 3 value to the permutation 1, 2, 3, you get 3, 1, 2. And this means that 3 and 1, these two values must be consecutive. And this means that this one, the value which is related to 2, may be far from this one. It's not necessarily consecutive to 3, 1, 2. And here you see you have a triple. You have a triple A, B, and I, and L. No. A, B, I. Another triple. 3, 1, 2, like this. Another triple, 3, 1, 2. So for each I, such that Pi equal J, you have you have certain number of triple. This one, this one, this one, and the number of such triple is exactly J, the indices of the block in red. So whenever I will have the parameter in the Q-analog of this history, I will have the sum of all the possibility, minus 1. So this parameter is going to be the total number of such a triple. Number of triple, total number is J minus 1 equal number of triple. So the sum of all the possibility minus 1 is going to be the total number of triple like this. So this will be a characterization of the Q-analog of all this story. So I'm talking about Q-analog. It's time to explain why this bijection is fundamental in the theory of orthogonal polynomial. So this refers to the class, another year, but But I just remind you, I make a complementary slide, one of the previous classes very fast. So I apologize, I will go slowly. So orthogonal polynomial. So definition of a sequence of orthogonal polynomial. Usually it's a definition with a measure, integral, all this. So this is formal orthogonal polynomial. So we have a sequence of polynomial in one variable with coefficient in a certain ring K. It can be integer, it can be polynomial in alpha, beta, gamma, it can be anything. There is one variable, a ring of coefficient. And we say that this sequence is orthogonal if and only if there exists a linear functional f. This linear functional send any polynomial onto in the ring. It's a linear functional and satisfying the three conditions here. The degree of Pn is n. Each polynomial has degree n. You have f of pkpl equals 0 if k is different of L. So it's kind of orthogonality for a certain scalar. This is a scalar product, f of pq. And f of p, if k equals L, then this must be non-zero. F of pk equals non-zero. So that's all. That's a formal definition.
We don't assume it to be 1.
Hmm?
Not assume.
No, or if you can normalize so that this is 1 or this is...
Or 1.
So if there exists a sequence of orthogonal polynomial, then f is unique up to a multiplicity. And if you give f, there exists at most only one sequence also unique to multiplicity of the polynomial. And to define f, a linear functional, it's sufficient to define on the basis of polynomial. So f of xn, we will denote this by mu n, are called the moment of the orthogonal polynomial. And usually the linear functional or the moment are defined with some integral, some measure, etc. But in combinatorics, we don't know how to go with the measure in combinatorics, so it's better to keep only the moments. We don't need all this integral analysis. So usually orthogonal polynomial was part of analysis, but now it's become part of combinatorics. There is many things where you can avoid completely the analysis, the measure, everything, and everything is formal. And so there is a fundamental theorem about orthogonal polynomial, about formal orthogonal polynomial, that the sequence of polynomial, I will take monic polynomial, which means that the coefficient of x power n is 1. Polynomial is starting with 1. So the degree of each Pn is n. It's starting with Pn equal xn plus something. So a sequence polynomial is orthogonal if and only if there exists some coefficient bk lambda k in the ring K. Bk start at k equals 0, lambda k start at k equals 1. Orthogonality means that there exists such two sequences such that the sequence of polynomials satisfies this three-term linear recurrence relation. See, you can deduce pk plus 1 is going to be time x times pk, so the coefficient, the biggest coefficient will be x power k plus 1. So minus bk pk minus lambda k pk minus 1. So this is the famous three-term linear recurrence relation. Every family of orthogonal polynomial, there is many, Laguerre, Hermite, Charlier, Askey-Wilson, Mexner-1, Mexner-2, Jacobi, Chebyshev. We have seen Chebyshev polynomial, first kind, second kind, etc. So all this sequence of polynomials satisfy a three-term linear recurrence relation. And conversely, if you have polynomial satisfying this, if you give the bk lambda k, then you get some orthogonal polynomial. So if you give me the moment mu n, I get a unique sequence of polynomial up to multiplicity. So I get a unique sequence of bk lambda k. And conversely, if you give me pk lambda k, I get the mu n, the moment. So there's a kind of correspondence. There is a correspondence between a pair bk lambda k and the moment mu n. But here we are only interested in the combinatorial aspect of orthogonal polynomial. So if you give me bk lambda k, give me an explicit expression for the moment in terms of the sequence bk lambda k. So there is a formal expression, which is the following. So define the Motzkin path. Just the Motzkin path. I don't need two colors on the level. And define the evaluation of the Motzkin path. To put 1 when you go up. Bk when you are at level k, and lambda k when you go down. Starting from my sequence bk lambda k, the sequence of this 3-term linear recurrence relation, I'm going to give you an expression of the moment. So first I start with weighted Motzkin path with this valuation. So for example, the weight of this Motzkin path is b0, b1 to the square, lambda 1 to the square, lambda 2. Each elementary step is weighted by 1 or bk or lambda k when I start with level k. So if you give me any Motzkin path, the weight will be a certain monomial in the variable bi and the variable lambda I. And then the fundamental theorem tells you that the moments, the f of xn, are exactly the sum over all Motzkin paths of length n, the sum of the weight of the Motzkin path of length n.
This is your theorem, right?
Well, it's a mixture with Flageolet, with myself and other people. Yet it's not clear. Well, the idea interlast each other sort of in 1980, and so it's equivalent by its the first bijective proof, yes, was given by your servitor. So you see, if you give me any bk lambda k, I get moments equal to this. So Laguerre, if you give Laguerre polynomial, so the moments are n plus 1 factorial. The moments of Laguerre are permutation, and the bk lambda k are equal to this. bk equal 2k plus 2, lambda k equal kk plus 1. So if you are a bijective combinatorist, you know that if you give bk lambda k, this is the sum of the weight of Motzkin path with this valuation must give you, total sum of all the weight must give you n plus 1 factorial. So there must be a bijective proof. Let's go to this path with the weight to permutation. And that's exactly the Laguerre history, which gives you this bijection to prove that if you have this, bk lambda k, then you get this moment, n plus 1 factorial. So I'm going to show you the relationship with this Laguerre history and this bijection between Laguerre history and permutation. So here we have this weight, and if you check, you can really check that 2k plus 2 here, I have k equals 0, so I have 2, 2, 2. You see the weight here is 1 by 2, 1 by 2, 1 by 2, so 8, 4, 4, 8. You can check it's 24. You have 24 permutations, the sum of all the weight for this valuation of Motzkin path. But how to transform this into column Motzkin path and the weight, the valuation, how to transform this to what I have done Laguerre history. So the transformation is the following. Because I have 1, I have bk which is linear, I have lambda k quadratic in k, I'm going to transform this into everything linear. So the bk is going to be, I am going to put blue and red to have the sum of these two valuations. And now the lambda k, which is quadratic in k, I put a product of ak minus 1 ck, where ak is the weight of going up, ck is the weight of going down. And you see each step going up is related in bijection with the step going down. We have done this already for the x factorization in Catalan. So every up step is put in bijection with the down step. So that the total product of these two weights is going to be lambda k. So if I have any two weight for the blue and the red level satisfying this condition, any two weight for the going up and down satisfying this condition, with lambda k equal the good and bk the good for Laguerre polynomial, then I can transform this problem into the following. So lambda k bk becomes this, and for the Laguerre polynomial you have bk equals this, which become with the 4 possible valuations, which become to this. So the moment, the sum of the weight of all this path is equivalent to say that the sum of the weight for the star weight with this valuation. And this valuation was exactly what we have done for the Laguerre history. So I claim that the sum of the weight of all these two-column Hodgkin paths, which we prove it's n+1 factorial, is the sum of the weight of all these Hodgkin paths with this quadratic weight, which is n+1 factorial. So I have proved that if I have this three-term linear recurrence of polynomial, the moment is going to be n+1 factorial, the sum of the weight of all the... So I have some paths. I define some history which are weighted paths. There is a valuation. Now the possibility is another weight which is between 1 and the maximum weight. And now I'm going to weight the Laguerre history. This is why I introduced the term Laguerre history, because at the beginning people was talking about weighted paths, but there is many weight. Because Laguerre history, I'm going to weight the Laguerre history, which is again a weighted path, etc. So now the term is, many papers use this term, Laguerre history, Hermite history, Charlier history. So weighted Laguerre history. What about the Laguerre polynomial? Have usually a certain parameter alpha. Alpha may be 1/2 or anything, but here alpha is a formal parameter, formal variable. So if you put the alpha, if you put alpha equal 1, you get back the weight of the Laguerre. But putting alpha, what does it mean? So you have to find AK, BK. So you have a choice. It's not unique to decompose my evaluation BK lambda K with alpha to decompose it like this. So the decomposition, which is going to be to do this transformation, but now with the parameter alpha. So here what I choose. You have a choice, but you mean to have a good choice so that you get a combinatorial interpretation. So I put B prime K, the blue level K plus alpha, the red level K plus 1, CK, AK when I go up K plus 1, and CK when I go down K plus alpha. So with these 4 possible weights, this is an arbitrary choice, I get back this valuation BK lambda K, giving the Laguerre polynomial. The sum of these two is equal to this, and AK minus 1 multiplied by CK gives you this. So now I go back to my Laguerre history. If I do alpha equal 1, I have everybody becomes K plus 1. So alpha is a parameter counting something. What does it count? Here it's count. I should take maybe the first choice. There is a certain probability of choice. So I put a weight alpha. Each time you take the first choice when you have a blue level. And here alpha, each time you take the first choice when you have a CK when you go down. So we have a certain weight on my Laguerre history, which is exactly this. You put a weight alpha, I repeat what I have done, when the choice pi equal 1, and when the elementary step is a blue step or a southeast step. And what happened, and this is equivalent to say that the element I is the left to right maximum element of the permutation. It's because this time you put one of these step, you put the value I in the first position, and you do not open any new position on the left. Imagine I is in the first position, but you don't, because of this possibility, you don't open a cell on the left. So it's finished. Your permutation will start with this value I. And then if you insert some new value, there will be nobody on the left bigger than the... So it's a left to right maximum element. Just think of this, and this is a characterization of left to right maximum element in terms of the possibility. So you see, usually left to right minimum element, we have seen in the inversion table, they correspond to the first choice. And the left to right maximum element corresponds to the last choice. Here you have to be careful, because if you take the first choice everywhere, this will not give you, this will give you more elements than the left to right maximum element. Only take the first choice when you have these two kinds of steps, and this will give you the left to right maximum element. For example, left to right maximum element, except the last one, which I insert in a different way at the end. So here is my example of history, 4 and 6. So let's look in the Laguerre history what happened with 4 and 6. The left to right maximum element are 4, 6, and n plus 1 equal 9, but I don't count this in the first choice. So I have only these two with the step omega 4 and omega 6 are going down and blue step, and the possibility is 1 and 1. So I satisfy this condition, satisfy exactly this, and this is only the only two left to right maximum element which are different from n plus 1. So you get a characterization of this element in terms of the weight alpha, of the weight of the history, so you can deduce the moment of the Laguerre polynomial with the parameter alpha are exactly the sum of the weight of the Laguerre history with this weight alpha, which we know now it's a left to right maximum element or minimum or etc. This is a Stirling number. Because I have to delete the n plus 1, I don't call it plus 1, so this should be alpha. If the first one should be alpha, alpha plus 1, alpha plus 2, but I don't consider the maximum element, so I have one alpha which is not at the beginning. So I deduce completely with bijection the moment of this Laguerre polynomial with the parameter alpha, and I have an interpretation of the parameter alpha in terms of the permutation. So restricted Laguerre history. So you go back to the general Laguerre history. So this n plus 1 factorial corresponds to this weight, and this corresponds to Laguerre with alpha equal 1. But there is also Laguerre with alpha equal 0. And I claim that Laguerre with alpha equal 0, in fact, the bk lambda k are different. They are exactly this. And this corresponds to n factorial. The moment of Laguerre index 0 is n factorial. And it's useful in all the theory, in the other use of the theory, to introduce restricted Laguerre history. Restricted means very simple, that we put alpha equals 0. So this means that there is no left to right maximum element. The only one is n plus 1. So this means that sigma 1 equal n plus 1. And the interpretation of alpha was counting the left to right maximum element different of the maximum. So alpha equals 0. There is no such element, so the only element is n plus 1. Sigma equal n plus 1, and of course, permutation having this is n factorial. So the bk is 2k plus 1, lambda k equal k to the square, so this is for alpha equal 0, and moment equal mu n equal n factorial. Sometimes it's more useful to use this restricted Laguerre. Sometimes enlarge, so it depends. For example, if I put parameter beta equal alpha plus 1, I have here alpha equals 0. When alpha equals 0, beta equal 1. So now it takes this weight, and then this give me, for restricted Laguerre, I will have a weight beta for each choice pi equal 1, where omega I now is different, is a red level or this. So I will go fast here. Just believe me that this is equivalent to say that this condition, that I is the left to right minimum element of sigma. So you have another characterization of minimum element on the history where I have sigma of n plus 1 equal 1. No, sigma 1 equal n plus 1 means that you always keep, all along the construction, you keep the first empty cell to be always empty. You are not allowed to put anybody in the first empty cell. So you are allowed to put somebody if it opens a new empty cell on the left. So this is a restricted Laguerre, is you always keep an empty cell at the beginning of your word, and at the end you put n plus 1. And believe me, the corollary you have this, and remark if you put alpha equal 1, then you get beta equal 2, and you get this. And so you get back n plus 1 factorial, and this is the proof. Sorry to go very fast, but it's related to some exercise on binary search tree, where you have also the same distribution, so all the word is unified, everything is related to putting a 2. This is this picture, this is the solution of part of the solution of exercise. Sorry, I'll go fast because I have 1 hour, enough hour, but this is just a complementary slide. So now we go to Hermite polynomial. So we have our big bijection between Laguerre history and permutation. I am going to make a special case. I am going to restrict the choice, restrict the valuation, and then I will get the moment of the Hermite polynomial. So Hermite, it's a sequence of orthogonal polynomial. You have seen many times Hermite polynomial, which can be defined like this: bk equals 0 and lambda k equal k. So it's a big restriction. You have no blue step, no red step, and lambda k. When you go up, the weight is 1, and when you go down, it's not k plus 1, it's only k. So it's a kind of very restricted Laguerre history. And then we know that the moment of the Hermite are on an even number, odd number of elements, it's 0. On an even index, it's 1 multiplied by 3, multiplied 2n plus 1, the number involution with no fixed point. So we have to prove bijectively that if I take weighted two-column Hodgkin paths like this, which is going to be a weighted Dick path, the sum of the weight of all these paths of length 2n must be the number involution with no fixed point. So I call an Hermite history. It's a special case restricting of a Laguerre history. So first we have a Dick path, because bk equals 0. And then you have a choice function. So P1, P2, P2n, it's a Dick path, such that if the elementary step is going up, then Pi equal 1. You don't have any choice. And when you go down, Pi related to the step omega I, when you go down from level ki to k minus 1, then you put the weight ki. You put the weight, the height of the vertex. So this is called Dick Hermite history, and I may show that the sum of the weight of all the Dick paths of length 2n is going to be the number involution with no fixed point. For example, I take this Dick path. Now above, this is a possible weight, the v of omega, the total number of possibility, 1, 1, 2, 2, 1, 2, 1, 2, 2. So this red number is when the height of the vertex. You put a 1 here because there is not at all any choice. And the blue numbers is any numbers between 1 and the red number above. So you can take the Laguerre bijection and put in force here, but there is a direct description of the bijection, which I give now. So involution with a fixed point, we can put this as a core diagram, like this. This is an involution with no fixed point. And then I'm going to give you a direct bijection between this weighted Dick path, or Hermite history, and this core of the diagram. So first, I do the following. I follow my Dick path. Each time I have a step going up, I put something like this. Each time I have a step going down, I put something like this. This is, remind you, the letter X, X bar of the Dick language. So this is the coding of my Dick path. Okay, of length 2n. Now I am going to connect these green half edges between themselves to get a core diagram, which is nothing but other than an involution with no fixed point. So I will connect them according to my blue number of choice. So I connect this and this. If I shift by 1 the choice, this to do Q-analogue. Sorry for the shift. I delete from all these blue numbers, I subtract 1. This to go directly to the Q-analogue. So this is 0, 0, 0, 0, 1, 0, 0, 0. So suppose I am in a certain step of the construction. I have connected some of the green things. This is the first connection because the possibility was 1. So I put 1. I put a 0. The possibility was 1. Now I take the next open edges going to the left, and I am going to connect this, maybe to this one, maybe to this one, according to the number of possibility. So the rule, you say, when you connect, you have to put some numbers on the choice. So there is 4 possible choice, which in the Q notation is 0, 1, 2, 3. In the previous notation, it was 1, 2, 3, 4. Sorry for the shift. And then you label this empty position from left to right. You have to make a choice. I can label them from right to left. It will give you something different. And then you connect according to the possibility function. So I take this one, and I connect because the possibility was 2. 2 minus 1 is 1. So this was the first position, second position. Now you take the next one, you connect them, and it was supposed to be in the first position. Now you take this one, there is only one possibility, you connect, and you get a core diagram, you get an involution with no fixed point. So this is the bijection between Hermite history and the core diagram, which give you proof that the moment of the Hermite are exactly this, knowing that bk lambda k are bk equals 0, lambda k equal k. Now I have shifted the index to give you, now in the country of Q-analog, to go the Q-analog of the history. So when I do Q-analog, the minimum, the first choice is labeled 0, Q power 0, so this is what I have shifted everybody by 1. So the Q-Hermite, so there is different Q-analog of Hermite. The Q-Hermite, one possible Q-Hermite is you just take the bk equals 0 and lambda k, a Q-analog of k, which is 1 plus q plus q2 plus qk minus 1. So this means that each time you take the choice number I, you have a weight q power I. So if you remember what we have done with inversion number and merge, each time the Q-analog was exactly the same. You have a certain number of choice, you label them 0 to maximum number of choice from any, if you label from left to right, or right to left, you get inversion number. When you label with descent and rises as a merge, then you get the merge. So what you get depends on the way you label your empty cell, but the important thing, abstract history, is that you have a certain number of choice. When you take choice number I, once you have labeled the possible choice, then you put q power I to be the weight. And then the weight of the history is q power, the product of all the q power I, which is q power, the sum of all the possibility. So what we have done here, you see, if I put a q power, the indices of the choice, I claim that the q power, I get q power, the sum of all this is 1. And I claim that 1 is the number of nesting of the core diagram. Nesting means, you see, there is 2 pairs like this. Nesting means this. So when I have done Q1, 1 was this position, then there will be a nesting, because this is not completed. So you can think by yourself. Exercise shows that each time you put a q power k, there will be k pair above the. If I could keep, there will be k pair above it, which give k nesting of the core diagram. So I claim that q power, this parameter, the q-analog of this, will give me q power, the number of nesting in the core diagram, the number of pair of chord which satisfy this condition. But now the power of the philosophy of q-analog of history, if you can now label from right to left. They are very good in this class. This is the crossing now. If you label from right to left, the q power, the sum, here q power sum is going to be 2, and there is 2 crossing in the. You can check that labeling from right to left, the q-analog will give you the q power, the number of crossing. So I have a proof that the number of crossing and the number of nesting are the same distribution, which in fact is exactly the distribution of the sum of the history, which is the total sum of the possibility when I start the possibility to 0. Yeah, it's so. Yeah. And this was a theorem. So some people make some paper for this to prove this. If you don't know Hermite history, then it can give you a paper in a respectable journal. But once you know the Bijection with Hermite history, then it's immediate. Because it's 2 different ways to label your free position. The same as inversion and merge, you see. So this is the philosophy of history. You get many different things when you label the. Same from Laguerre. We are going to make a q-Laguerre, and the different labeling give you different interpretation. So when I take sum of the history, the sigma of pi minus 1. The total sum of all the choices. Even there is more. Right? This philosophy of history, exercise. The philosophy. Wait, it's coming. I'm ready to always each lesson he's asking the next 3-4 slides, but before exercise, before going to Q-Laguerre. So even I can take the Qt analog. the double polynomial crossing and nesting, and this polynomial is symmetric in Q and T. So give a proof of this because it's referred to two different labeling, but there's a symmetry between Q and T. Think of this with the two different labeling of Hermite history and the core diagram. So don't try to publish this, but it's it's already been done in a respectable journal to have a proof of this without using anything but Hermite history. Now Q-Laguerre. So Q-Laguerre's weighted history. I put the weight. We have put for Laguerre alpha, the weight alpha. Now I put the weight Q. So I don't know, there is different Q-analog of Laguerre polynomials. There is continuous, discrete. There is different also continuous, discrete for Hermite. I don't know, but this is a certain Q-Laguerre. I will call this Q-Laguerre first class number 1. So if you take BK, just a very natural way for Q-Laguerre is to take a Q-analog of each of the term of BK lambda k.
The Q-analog always tells you how to split. Lambda k is...
Yes, it's already splitted in, this is B prime cam, yes, this is splitted. This is already splitted. Don't take a Q-analog of 2k plus 2, right? And then, so if you take Q-analog like this, this is exactly, this was the 4 possible paths type of step in the path, 4 possible, and this was a choice function. So what you get, the Q-analog, if you put a Q, each time you have choice, you take choice number pi. So if you put a Q, the total weight will be Q power the sum of all this. So this will be the Q-analog of Laguerre, and the sum of the Q-analog of all this history will give you exactly the moment of the Q-Laguerre. So let's give an example. See, so from this valuation, I go to the 2-column Hodgkin path. This is the Q-analog of the Laguerre history. So let's give an example of like this, you see. So this was the second definition of the Laguerre history, where I put some new numbers each time in an empty cell, and then each time you put, this was the possibility function, pi. This was the first, second, first position. So I shift everybody by 1. So this is what put in cell position 0, position 1, 1. So the total weight of the history is q power the indices of all this, which is q power 4. So this permutation will be weighted q power 4. And in fact, if you go back to the other characterization with triple, the number of patterns 3, 1, minus 2, you remember the pi was 1 plus the number of patterns. So pi minus 1 is the number of patterns. So the Q-analog I am doing here is exactly the parameter, the number of such patterns in the permutation. So usually in many papers, people prefer to work with this instead of going back to the abstract history. But what I claim is that this characterization, you have given a certain order in the empty position from left to right. And if you do the same as for major, to make some more sophisticated numbering of the free position, maybe you get some other parameter, which has again Q-Laguerre. But for me, the abstract Q-Laguerre is just the sum, Q power, the sum of all the sum of the possibility. It does not depend on the labeling of the, so it's an abstract level, and if you give different labeling, then you get this parameter. For Hermite, you get number of crossing, number of nesting, so you can get many different parameters, and make some paper if you forget everything about the way you get it, with the history, the labeling, and you can make some beautiful direct paper. Okay, some complement now. The Q-Hermite and Q-Laguerre second kind. So there's a continuous, I don't know if it's continuous or discrete. So Q-Laguerre second kind, but why not to take, if you take mu n equal the Q-analog of n factorial, the Q-Laguerre history, you don't get at all this Q-analog. You get another Q-analog, and then, surprisingly, the BK lambda k are the same as for the first Q-Laguerre, but you multiply by this. This is difficult to prove, that the sum of all this with this weight, so you have You multiply by this. So not only you take q power I, where you take position I, but you multiply by q power the number of choice you have. And if you take bk lambda k, then you get exactly this. And then this, I have no time to define you. There is another kind of history, what we call subdivided Laguerre history. It's again some history such that the sum of the weight is going to give you n factorial, but instead of working with two-column Hodgkin paths, we are working with Dick paths. With only Dick paths, there is a certain weight. It's not the weight lambda k equal k, because it gives you a Hermite polynomial, but it's the weight lambda k equal half of k. The smallest integer is k divided by 2, the integer part of k divided by 2, if lambda k equals this. If you put this, then you get again n factorial, and then there is another bijection. It's more complicated. It's not, I will not do this in this class, but maybe in the class of orthogonal polynomial, I will need this bijection. And with this bijection, you can prove both at the same time that you have this n factorial, and you have the first, the other also q-analog, the first q-analog. And also you can do the same with parameter beta, counting the stealing numbers, the left to right moment. So you have a q-analog with a beta. So you have the q-Laguerre index beta, and everything works very well for both q-Laguerre, Laguerre 1, Laguerre 2. So this is the q-Laguerre of the Laguerre history, Laguerre 1. And you see the moment of this q-Laguerre is much more complicated than the moment of the q-analog of 8 factorial. So this is at the richest level. So the moments are not obvious at all of this. And this moment comes from the study of the, in physics of the PASEP. So there's a very strong connection between this q-Laguerre polynomial, the first one related to the Laguerre history, and the PASEP. So you remember when I was the complement of the TASEP. TASEP was the particle enter on the left with probability alpha. They go outside with probability beta, and each particle is moving on the right, and at most one particle in its cell. Now the PASEP is particle can move backward with the probability q. Now I claim that the partition function, in physics there is a partition function, there is stationary probability, there is a certain function, partition function. We have seen in the case of Catalan number, the partition function was the sum of the weight of all was Catalan number, and with the parameter alpha beta it was the sum of all the weight of binary tree, with alpha power the length of the left branch, beta the length of the right branch. So with the q, now the partition function, it becomes the q-Laguerre, the moment of the q-Laguerre, the first kind, the q-Laguerre of the q-Laguerre history. And the alpha beta becomes a double distribution related to left to right minimum to Stirling number, and so all this work very well. And the q is really, it's not the q-analog with the inversion number, it's a q-analog for the Laguerre history, which is play a fundamental role in the PASEP. So there is 100 of papers on the PASEP in physics, and everywhere there is this very important q-analog of Laguerre, and there is extension with the general model to go to Askey-Wilson polynomial. So was not to do the same for Hermite, instead of the q-Hermite with number of crossing, number of do the q-analog of the direct q-analog of 1 multiplied by 3 multiplied by 5, the number of involution with no fixed point, analog of q-analog of n factorial. So for q-Hermite, then bk equals 1 and lambda k, exactly the same phenomena appear. It was the same valuation as for Hermite history, but multiplied by q power something. So it's discrete. There is a different discrete q-Hermite. That at least in this class there is only two q-analog of Hermite and or continuous. So this was the first giving the involution with no fixed point, with number of crossing, number of nesting, and again in this the moment here is really complicated. It's not at all. It's the same phenomena as for Laguerre polynomial. You see, and this was all d'identité, and Penaud gave a bijective proof of this moment of the. So you see the philosophy of this history in q-analog. So we have 4 q-analog. You have the 2 q-analog of Laguerre, the 2 q-analog of Hermite, and each time I am doing each time I'm doing a Q-analog, it's the first Q-analog is you put Q power number, the choice, if you take choice number I, you put Q power I as the weight. This was for the Hermite and for the Laguerre. And now the second kind, which gives you the n factorial Q-analog of n factorial Q-analog of 1 multiplied by 3 multiplied by 5. Second kind, you take the same Q power the I, choice number I, and multiply by Q power the total number of choice. So there is a certain analogy between the two kinds of Q-analog, and again, this philosophy, see what we have done for Laguerre history, it's related to, you remember permutation was solution of the differential equation, y prime equal y2, and I get the solution of the differential equation was with the trees, a binary tree, increasing binary tree, and so this philosophy of history can be applied to any system of differential equation. And we have seen in the complement of control theory, it go very, very fast, but there was a tree growing with, to get the iterated integral, and this tree growing again was an history where you fill up, you have some empty cell, and you fill one empty cell, and maybe you open many, many more empty cells. For example, for the system of the differential equation satisfied by a Jacobi elliptic function, there is 3 colors in the empty cell. Each time you fill up a blue empty cell, you open a red and a green. Each time you fill up a cell of one color, you open two new cells with the two other colors. So you can make more, you can play with the color, with the rule. So all this philosophy of history, we have applied this to solve differential equation in control theory with the forcing term and iterated integral. So it's the same philosophy. A very special case is a differential equation y prime equal y2, which give you rise to the Laguerre history and all this. So I'll finish with some complement. So Laguerre history and orthogonal Sheffer polynomial. This was another complement. I went very fast, but now I have more time, 10 minutes more, and I can go slower. So you remember that this was the definition of Sheffer polynomial. And if you intersect the two classes of orthogonal polynomial and Sheffer polynomial, then there is only 5 such polynomial. The Hermite, the Laguerre, Charlier, Baxter 1, Baxter 2. So there is no parameter. Laguerre has 1 parameter, Charlier has 1 parameter, Baxter 1 and 2 has 2 parameters. And what is interesting is that the moment of the Charlier are exactly number of partition, the Bell number, and the parameter is counting partition by the number of blocks. So here is Hermite, here is Charlier, the Bell number, the Laguerre, there is some parameter, and the 2 Mexner, here is Baxter 1, Mexner 2, and special case of Mexner 2 is the secant and tangent number. Special case of Mexner 1 is it's partition where you put a total order on the block of the partition. This is called the ASCII tableau. It's a classification of classical orthogonal polynomial. Each time you go up, there is, at this level, there's a Q and 4 parameters. This has really the polynomial related to the Passet model with 4 alpha, beta, gamma, delta, and Q. Each time you go down, it's like you lose something or you make a limit case with change a variable. So everybody go down. And so the Sheffer polynomial are here, and here. And I claim that you can study all the combinatorics of these 5 polynomials. Everything can be done with Laguerre history. What you have to do is maybe to make a restriction, like here, secant number, to make a restriction of the history, like we have done for Hermite. There was a big restriction. And you put some weight on the history. Weight alpha, weight for the number of blocks, or 2 weight here, beta, gamma. So the Laguerre history is a central bijection to get all these 5 Sheffer orthogonal polynomials. For example, Hermite is a special case of Laguerre. Each time you, instead of taking chord diagram, each time you put a double vertex, when you go up in the path, you have a weight 1, so you always put in the first position. Each time you put a leaf, then you stop. So you can, this is a special case of the Laguerre, the trees obtained by Laguerre permutation. Charlier, you can also see this as a special case of Laguerre history by getting this kind of trees. Each of these branches is going to be the block of the partition. So you can really, Charlier, Hermite, all this, get some special case of Laguerre, or maybe Laguerre itself with some different weight. And you can put, you can do all the Q-analogue also of this phi class of Sheffer polynomial. Everything worked very well, and so this is why I insist on this bijection Laguerre history, because it can be useful for many things in the combinatorial theory of orthogonal polynomial, and also for the PASEP for physics. And I will finish with the Baxter permutation. So this is a nice application of the bijection. So Baxter permutation, it's the following permutation. This was introduced a long time ago, but many papers now are working with some kind of combinatorial object, which are counted also by this Baxter numbers, the same numbers of Baxter permutation. It's a kind of super Catalan numbers. There is Catalan behind this, but really more deep, more complicated. So Baxter permutation, it's permutation which avoid this pattern. There is no 4 indices, I, K, L, J, such that I less than K less than K less than J, with sigma of L is less than sigma of I, and sigma of J is 1 plus sigma of I. The two values here are consecutive. It's 2 consecutive values, and then sigma of K is here. So you are not allowed to have this pattern. This is the first condition. Second condition, you are not allowed to have the symmetry of this pattern. So if I take the symmetry of this, it's also forbidden. Yes, then let's do it again. Okay, so this is called Baxter permutation. So this is an example of a Baxter permutation. And then in 1978, after a terrible papers, a terrible recurrence relation, it was a terrible papers, these 4 people find this formula for the total number of Baxter permutation. And then further, then this individual term, sum over K, this term counts the number of Baxter permutation having K minus 1 rises. So now with the Laguerre history, the bijection today, we can have a simple, easy proof of this. If easy, you must know something for the chapter of the last week to be able to do everything. So first, let's do the Laguerre bijection for this kind of permutation. So you can characterize completely the Baxter permutation in terms of the choice function. Don't see the detail. You see, when you have this kind of going up or a double or a blue level, then f of the choice function is equal to this or maybe this plus 1. And if you have these two kind of steps, the choice function is this or this. So this means it's a lazy choice function. Once you have made the choice f of I, you are going to move, maybe keep it or maybe move to the left, move to the right, take the same choice, maybe increase by 1, maybe decrease by 1 according to these two possibilities. So this is a characterization. It's a nice characterization in terms of Laguerre history. So here is my Baxter permutation. Here is a related Laguerre history. So you have your 2-column Hodgkin path, and here is the choice function. So you see the choice function is something which doesn't move too much. It's really lazy choice function. It's satisfying these two conditions. So there exists. So now you have to count such a pair of a 2-column Hodgkin path, and this blue point, which seems to be a little rather complicated. But now we know that 2-column Hodgkin paths are in bijection with staircase polygon. So let's do it. So here is my 2-column Hodgkin path. Here is a staircase polygon, and now the width, this different width, is exactly the height in the 2-column Hodgkin path. So the number of possibilities, my blue crosses is here. I have 1, 2, 3 possibilities. So you see these blue crosses. For example, there is something in the middle at number 4 between 1 and 3. So you just put it, your blue crosses here between 1 and 3. This is first possibility, second possibility, third possibility. You just repeat your choice function inside this staircase polygon. And now the magic of the combinatorics is that the condition F, the blue condition, become a path between the two paths. So this strange condition which is here, once you go the bijection from two-column path to a staircase polygon, it's become exactly the condition that your blue numbers, they form a path in blue going north or east between the two paths, the upper path and the green path. So you have to count the triple of such paths. You see, for general permutation, this is a general permutation. The blue path can be anything. It can go check, check, check. But for Baxter permutation, the blue path is really only north or east step. So you have to count such triple of paths. So I anticipate on the chapter 5. Yeah, I have to count triple of paths. I just, from this picture, I just move them a little like this. Now it's better to add to put the whole diagram and to put some, to add this. It's more convenient for, yes, you will see in chapter 5 why we do this. And then you have some paths, triple of paths starting from A1, A2, A3, finishing in B1, B2, B3. And so then I apply, if I take a 3 by 3 matrix, the term a 3 by 3, I take all the paths starting from one of this point, ending to one of this point. So I have a 3 by 3 matrix. I have some coefficient here. And in fact, it's a minor of the Pascal triangle. Here is a Pascal Pingala Meru triangle. And I am taking a 3 by 3 minor of 3 consecutive columns, 3 consecutive rows. Now you will see in chapter 5 that this is the determinant. The number of triple of paths which are non-crossing is this determinant. This is the total number of paths going from A1 to B1, from A1 to B2, from A1 to B3, from B1 to A, etc., etc. I have this 3 by 3 determinant, and then this 3 by 3 determinant is equal to this. And you will see again in chapter 5 that we have a nice proof of this, because this is the hook length formula appearing. And so there is a hook length, there is related to Young tableau, and this gives you this gives you a proof. And you have to show that the K is going to be the number of rises of the permutation, and this works. The parameter rises is preserved in the bijection. But this reminds you something. When I have two paths, there was a 2 by 2 determinant. This was the Narayana numbers. So this is, see, 3 by 3. So the sum of all the 2 by 2 determinant in the same row give you Catalan number. The sum of the 3 by 3 gives you the Baxter number. And then many, many papers, totally different objects at permutation, are also counted by Baxter numbers. And now I'll finish this course today by telling you that the number of Baxter permutation, which are at the same time alternating, the alternating Baxter permutation are equal to, if n is even, is Catalan number Cn multiplied by Catalan number Cn plus 1, and if n is odd, or maybe the reverse, is the square of Cn. The square of Catalan in one case, and Cn plus 1 in the other case. This is the Baxter alternating permutation. I don't give you this as an exercise. It's maybe you can try, but it's a pair of dict paths, a pair of three, are counted by alternating Baxter permutation. Maybe you can try to prove this. There is some old paper 20 years ago or 30 years ago. But so this is nice relating. You see, Baxter is closely related to Catalan, but it's deeper than Catalan. Okay, thank you very much. Next week we start with Robinson's RS.